Welcome to this session. Last class 2 we have discussed about parallel transport, and today we will see the second theorem. Theorem 2. So let me write theorem 2. Let S be an n surface. Let S be a n surface in Rn plus 1. Let P comma Q belongs to S, and let alpha be a parameterized curve in S from P to Q, then the parallel transport P alpha from SP to SQ along alpha is a vector space isomorphism preserving dot product preserving dot product. So this theorem means that S be an n-surface in Rn plus 1 and P comma Q belongs to S, and let alpha be a parameterized curve in S from P to Q, then the parallel transport P alpha from SP to SQ along alpha is a vector space isomorphism preserving dot product. So what do we want to prove here? We want to prove that P alpha is a isomorphism. For that, we want to prove P alpha is a linear map, P alpha is 1 to 1 and on to. And second thing, we want to say prove that this parallel transport preserves dot product. That means P alpha of V dot P alpha of W is equal to V dot W for all V comma W belongs to SP. So let us write in brief. That is, we want to prove first one, P alpha is a linear map Second one, P alpha is 1 to 1 and on to. Third one, P alpha of V is equal to P alpha of V dot P alpha of W is equal to V dot W for all V comma W belongs to SP. So it is nothing but P alpha of V dot P alpha W is equal to V dot W for all v comma w belongs to Sp. So this is the thing we want to prove here. So first we will prove that this is going to be parallel transport is going to be a linear map. So proof of the first one. Let alpha from closed level AB to S be a piecewise smooth parameterized curve smooth parameterized curve from P to Q from P to Q. If V and W are parallel vector fields parallel vector fields along alpha then we know that so are V plus W and CV V plus W and CV for any C belongs to R. So any C belongs to R. So it follows that P alpha of V plus W is equal to V plus W of B. That's equal to V of B plus W of B, right? So plus W of B. Now this can be written as P alpha of V plus P alpha of W, and P alpha of CV is equal to CV of B. By definition, that's equal to C into V of B. That's equal to C into P alpha of B. C into P alpha of B. For every V comma W belongs to SP, comma C belongs to R. Thus P alpha from SP to SQ is linear. So we have proved that P alpha from SP to SQ is linear. Secondly, P alpha, we want to show that it is 1, 1 and on 2. So P alpha of V equal to 0. So which implies P alpha of norm of P alpha of V equal to 0. Which implies V of B equal to 0. Norm of V of B equal to 0, which implies norm of V of A is also 0. What's the reason? Since V is parallel along alpha, therefore norm of this V is equal to constant. So this is the reason. So this implies norm of V equal to 0, which implies your V is equal to 0. Thus P alpha of V equal to 0. Thus P alpha of V equal to 0 implies V equal to 0. So P alpha is 1 to 1. Therefore P alpha is 1 to 1. So these are going to be the n-dimensional vector spaces. So we can easily conclude that it is onto. We know that a linear map from a n-dimensional vector space to another is 1 1 if and only if it is onto. It is another application of your triangularity theorem. Thus what we got is P alpha from SP to SQ is 1 1 and onto. So next we want to prove that this parallel transport preserves dot product. So third one, since V and W are parallel, the vector space V and vector field W are parallel along alpha, so is V dot W. So V dot W is a constant along alpha. Let's study these properties. Now P alpha of V dot P alpha of W, this is equal to V of B dot W of B. Okay, now this is equal to V dot W V dot V dot W of B. So P alpha of V and P alpha of W. So I have wrote here, I have made some mistake it seems. So yeah, I should write here now. So it should be P alpha of V and this should be not vector fields. So P alpha of V and W. Okay. So P of V dot P of is equal to V dot W of B. And this is nothing but V dot W of A also. Reason is same. Okay, since V dot W is a constant we have set. So this is equal to V of A dot W of A. And V of A dot W of A is V dot W. So it is V dot W. So we have proved that this parallel transport preserves dot product. So today we have discussed only one theorem. I hope you may understood this very well. So I'm winding up today's session. Thank you for your patient listening. Thank you.